All right, congratulations, you're taking calculus. So what is calculus? Well, calculus is basically the study of functions and their rates of change. And when we think of functions in this class, there are going to be two ways that we should really be thinking of them. First, we can think of functions as a relationship between two quantities or variables. Oftentimes we'll be thinking of this as two real-world quantities that are somehow related to each other. Or we will think of functions as sort of a geometric picture, as a curve in the xy plane. We have a function, we get a graph, the graph is a curve in the xy plane. Now the fundamental concept that we're going to be studying in Calculus 1 is something called the derivative. And what is the derivative? Well, we're going to spend a lot of time talking about what that is. But throughout this class, I want you to keep two phrases in mind when you think about what a derivative is. On the one hand, a derivative is a rate of change. That's in the context of thinking of a function as a relationship between two quantities or variables. A derivative tells us how one of those quantities changes as the other one changes. Or we should think of a derivative as a slope of a curve. This is thinking of the geometric picture. We think of a function as corresponding to a curve. The derivative of that function will be the slope of that curve at a particular point. So that was a jump cut you're going to have to get used to it. This is not going to be really slick production values. I'm going to do my best to make it look nice, but what it is. Anyways, rate of change. When we think of a derivative as a rate of change, our motivating example is often going to be velocity. This is a rate of change of position with respect to time. Now, you've probably studied this before, and well, what is the average velocity of an object? Well, it's its change in position over a certain amount of time. So if I can measure an object from time A to time B, and I see where it changes from point A to point B, well, I take the change in position, divide by the change in time, and that gives me the average velocity. Well, when we're looking at the derivatives, we're actually looking for something better, in a sense, than the average velocity. We're actually looking for the instantaneous velocity. That means if I were to take the object and maybe watch a video of the object that's moving through space, pause it at a point and say, what is the velocity of the object at that exact moment? That's what I mean by instantaneous velocity. Well, how do I do that? Computing average velocity necessitates talking about a change in time. But if I freeze time, there's no change in time. So what am I going to do? Well, the way we're going to think about instantaneous velocity is it's going to be an infinitesimal change in position divided by an infinitesimal change in time, where infinitesimal means to us infinitely small. So I'm imagining that I'm letting time move in infinitely small quantity, seeing how much an object moves, taking that ratio, and that will give me the instantaneous velocity. Now, when we think about the slope of a curve, what we mean is the steepness of the curve at a particular point. So over here, I've drawn a curve, and we can, we can't really say precisely how steep it is at varying points, but at the very least I can say that over here it looks like it's steeper than it is over here. It appears to be getting less and less steep until at some point it starts decreasing a little bit, and then it turns around and starts increasing. So it's positively sloped, then the slope gets smaller and smaller, eventually it's negative, then positive again. Well, how do I make that more precise? When I talk about the slope of a curve at a point, what I'm really talking about is a tangent line. That's this line here in green. So if I want to talk about the slope of this point right here on this curve, I'm going to talk about the slope of the tangent line. The tangent line is the line that best looks like the curve at this point. It just touches the curve without going through it. It just meets that point and keeps going. Just hits it once right there. Now we should think of the tangent line as really being a line that goes through the given point and another point on the curve that's infinitesimally small away, so just a slightly farther away point than the one that I've drawn here. Now, if we think of it that way, then we can actually sit down and maybe try to compute its slope, because to compute the slope of a line, I need 2 points. So here, the slope of the tangent line is really an infinitesimal change in y over an infinitesimal change in x. This looks a lot like the velocity problem. Okay, so we've seen that both in the context of velocity and in the context of steepness of a curve at a point, we need to talk about infinitesimal quantities. Well, we need some machinery to be able to talk about infinitesimal quantities. This is math. We need to make this logically rigorous, mathematically accurate. I can't just make up infinitesimal quantities and start playing around with them. I need to be dealing with real numbers and real things. Well, how do we do this? We introduce something called limits. And limits are going to be the focus of Chapter 2. We're going to be looking at these over the next 6, 7 lectures or so. But what I really want us to get away from this first video is this first question. What two phrases should I think about when I think of the word derivative?